All right, I want to welcome everyone to MIT Inotherm, the International Colloquia on Thermal Innovations. Today, we have a special speaker, Dr. Ravi Prasher. He's going to be talking to us about dynamic and tunable thermal storage and transport. Um, I am Professor Ashegun Henry, Associate Professor in Mechanical Engineering at MIT, and one of the co-organizers of Inotherm. Today is going to be a presentation for about 45 minutes to an hour. Then we'll have some discussion for about 30 minutes or so. Please use the Q&A button to submit your questions to the speaker. And then we will feed the speaker, I'll host, and we'll feed the speaker questions and have him respond. We are recording, and these recordings do get posted to YouTube. It may include or may not include all of the questions that are answered today. The next webinar coming up on the 28th of April is a panel, Opportunities in Nano-Engineered Surface Designs, with Doris Vollmer, Demos Polikakos, Nenad Milkovic, and Yas Takata, and Dan Preston. If you have not, please go ahead and join our mailing list. And again, please give us suggestions if you have suggestions of speakers or topics that you want us to cover or have on Inotherm in the future. You can also access past videos and Q&A on the website. So today's speaker is, again, Dr. Ravi Prasher. Ravi has had an amazing career. He's a thought leader and mentor to me as well in our area. He's the Associate Lab Director of Energy Technologies and the Interim Division Director at Cyclotron Road at Lawrence Berkeley National Lab. He's also an adjunct professor in the Department of Mechanical Engineering at the University of California, Berkeley. He joined Berkeley Lab in June of 2015. Prior to that, he was the president of product development at Sheetec, a startup that was developing solid-state thermoelectric energy converters. He relocated to India for a while to develop these technologies for the rural Indian market. And earlier, Ravi was, before that, he was one of the first program directors at the Department of Energy's Advanced Research Projects Agency, ARPA-E. While there, he created two programs. One was the Building Energy Efficiency Through Innovative Thermal Devices, BEAT-IT program. The second was the High Energy Advanced Thermal Storage program. Prior to joining ARPA-E, he was the Technology Development Manager for the Thermal Management Group at Intel. He was also an adjunct professor in the School of Engineering at Arizona State University from 2005 to 2013. He's had a number of very, very seminal and important contributions to the field of heat transfer, and we're very excited to hear his talk today. So Ravi, please go ahead and share your screen, and we'd love to hear from you. Thank you.
Just one second. Okay, can you guys see it?
Yep. Yeah.
Okay. Good. Thanks, Asha, for the kind invitation to this webinar. I want to first of all thank Professor Dang Chen, who is a chair for this colloquium, and I think it's an amazing vision from MIT and amazing thought leadership from Gang, which he has always provided to the community in terms of research and where we should go. And in that direction, in the similar fashion, this is a new way of disseminating knowledge from broader community to all over the world. So I want to take this opportunity to thank him for that. And I also want to thank him that he has been a big mentor to me. And when I was a junior scientist, I learned so much just by reading his papers. Now with that in mind, so let me get going. Thanks again for inviting me for this colloquium. What I'm going to talk about today is hopefully will be of interest to the broader thermal science community. Is a topic called dynamic and tunable thermal storage and transport. And hopefully I'll show you why it is important first of all, and how if you have this kind of a system or a material, how it can be very impactful. And then later, half of the presentation will be more towards what are some of the open science questions and what are some of the things that my own group is doing to solve some of those questions. All right, so before I get going, this is I want to show you, and I think this is not a news to this audience, that we are facing a significant urgency here. So one of the main reasons we want to work in these technologies is to solve climate change. This is a graph that came out from National Academies, which basically tells you that if we want to remain below 2 degrees Celsius global temperature rise, which has been agreed upon in the Paris Climate Change Accord, then we better start dramatically reducing greenhouse gases, okay? And that would basically mean that we have to implement significant amount of renewable energy resources on the grid. And that's where energy storage becomes very important, and I'll talk about that later in more details. Second one is that roughly the available CO2 budget before we hit 2 degrees Celsius is roughly 1,000 gigatons. And if you do the math, right now we are emitting roughly 40 gigatons of direct CO2 worldwide and roughly 10 gigatons of other greenhouse gases. If you do the math, what we end up with is that we have roughly 10 to 20 years before we hit 2 degrees Celsius rise. So we don't have much time as a community. So one thing which I think a call to action to all of us, all innovators working in this area, is that we need a holistic science to systems research paradigm. So, the linear paradigm of, okay, having discovery and then maybe invention, then development and a system design and a demonstration, we just don't have that luxury anymore. And that's why it's very important, at least personally to me, and I think to quite a few in the community, is looking at both science, fundamental science and system science together and giving a lot of feedback to each and figuring out how we can accelerate the development. And hopefully I'll give you some flavor of that during this talk today. All right, so moving on, as I said, we will require a lot of renewable energy in the grid. It's already happening in some places. For example, in California, there's significant amount of renewable resources in the grid, but it is coming with its own challenges. Here is data, for example, in particular day, the yellow here is solar resources on the grid. It gave more than 50% of the energy. Electricity was coming from solar. However, as you can see, the wholesale price of electricity during the same time is negative. The reason is very simple. This is also widely known as a duck curve problem in California. The reason is very simple. We are producing a lot of renewable energy here. However, you're going to use most of the energy later in the afternoon. So there are no takers for this electricity. And to make the grid, to keep the grid stable, California as a state has to give money to the neighboring states to take the electricity away. So again, if we have storage, then of course we don't have to do this, and then we can store the energy here and then you can use it later during the day. So energy storage, as very well known, is one of the biggest technological challenges. Now there are two ways to do it: the supply side energy storage, or you can also store the energy in the demand side. My talk will focus more on the demand side. But again, thermal energy can also be used for supply side energy storage. In fact, Ashegan himself is working on some of those ideas. So before I delve into details, what I want to acknowledge my collaborators, because you will see a breadth of work that I will be presenting here, and it's in collaboration with many colleagues. I collaborate quite a bit with Professor Chris James at UC Berkeley, Dr. Suman Kaur and Dr. Gao Lu and Dr. Anwar Jain at Berkeley Lab, and then with Dr. Roderick Jackson at NREL. And a lot of the work that I'm presenting today has been funded by the Buildings Technology Office of USGOE. All right, moving on. I think it's widely accepted that with more and more penetration of renewable energy, the kind of storage that will be needed will vary all the way from hourly storage to days and weeks to seasonal storage. There was a nice paper that came out from Paulo Albertus when he was at RPE. So we will need hourly storage. Again, the line differentiating is a little loose, but I would call let's assume less than 10 hours is hourly storage. And then a long duration storage is greater than 10 hours, which is days, weeks, or even seasonal. Okay. And the economics of storage depends a lot on the duration of the storage. Okay. Now let's pose a very simple question that if today, hypothetically, let's assume 2020 or 2021 now, suddenly the whole electricity grid becomes renewable, supplied by 100% renewable energy, how much of energy storage, short duration and long duration will be needed? This is for United States. This is a study which came out from Caltech and Carnegie Institute. This does not assume building heating, electrification of building heating, which is another major driver in the future in terms of load on the grid, and I'll touch upon that later. But if we ignore building heating and you assume the demand is only 2020 demand, then short duration storage is of the order of 750 to 1,000 gigawatt hours. That's a huge number. And the long duration storage is of the order of 180 terawatt hours. Okay, so these are very huge numbers. And then if you look at how much of the storage is going to where, right? So today, this is the data, that was the data for United States. Buildings consume 74% of electricity in the United States. Okay, that means rule of thumb, roughly 75% of that energy storage is going to support just building loads. Okay, cooling is on rise in the world, right? Building cooling. This is the data. Peak electricity demand just to satisfy air conditioning demand. In China, it's already approaching almost a terawatt, okay, 800 gigawatts right here. India is rapidly increasing, right? Today, the world electricity capacity is 7 terawatts. Just imagine, this is just India and China. And then we add United States and other parts of the world. Significant peak electricity demand is driven by cooling, okay? So that's one big trend. Building heating will get electrified using heat pumps / resistive heaters or joule heaters, okay, in most of the developed countries. It's happening even in United States. So it is expected that in the future, cooling plus heating will be more than 50% of the electrical load in buildings, okay? Just something to keep in mind. Already, there are some predictions coming out that the peak load, right? Electricity, the peak load of electricity typically happens during summer, rightfully so, because there's a lot of AC demand during summer. So this is the pie chart tells you where it's happening. As you can see that this is summer. However, in 2050, with electrification of heating, we start seeing peaking demand even happening in winter. So these big blues, this winter peaking. In Northeast, a lot of peaking electricity demand will start happening in winter. Okay, so that's primarily driven by heating. So again, peak means there's a time shift needed, right? Suddenly there is a huge increase in power. That's why storage again becomes very important. Because if the peak of demand does not coincide with peak of electricity generation coming from renewable energy, there's going to be a mismatch. And that's why storage is going to play a very, very big role. Now this is a thermal colloquia. So I want to pose a simple question. Okay, I showed you earlier that, okay, we need a lot of storage. Let's ask a simple question. How much of that storage will be needed to provide building heating and cooling? A lot of other loads, right? And to my surprise, this was not a question which has been posed before. And so I'm working with the colleagues at NREL, and they have done some fabulous simulation. And we are still working on that, so we have not published the work yet. But what they have done is that they flipped the question. So far, most of the study has come from the supply side. So you figure out from supply side that I need this much of storage. Let's flip it and say, okay, I'm going to look from the demand side. So what I'm showing you here is typical US summer and typical US winter in 2050, assuming 100% renewable energy on the grid. The gold is the non-thermal load in the building, and the red is the thermal load. And this line, the black line, is the supply curve. This is for the case of 50% solar and 50% wind. Okay. Then we have done the analysis for different combinations of wind and solar, and the story changes there. But you can clearly see that you have more electricity produced here, except you don't have that much of demand, and you have more demand here on the shoulders. So definitely you need storage here, okay? That's one. And then you also see that almost all the non-thermal demand can already be met. So it's the thermal which cannot be met. In winter, you have, again, more electricity coming during the middle of the day, but you have requirement in the summer, in the evenings and also in early morning, okay? Again, you have more demand here and here, more supply here, so you need storage. So then we did some analysis, and what we found out the total storage needed for heating and cooling in a 100% renewable grid is in excess of 1,000 gigawatt hours just for providing heating and cooling for less than 10 hours. Okay, this is a short duration storage. This is equivalent to roughly more than 20 plus million EVs. Okay, this is just United States. And the long duration storage needed greater than 10 hours for heating and cooling is 100 terawatt hours. In fact, you should remember it's a question of resiliency as well. What happened in Texas recently was mind-boggling, right? Temperature was sub-zero, and the heating was one of the biggest energy needs during that time. All right, so moving on, let's ask a simple question. Is lithium ion the answer? So there's a very nice paper which has come out that if you have 50 terawatt hours of energy storage needed worldwide, what I showed you earlier is only for United States. You can multiply that with the number of demand across the world. So this study basically found out, I'm just going to give you the punchline, that the achievement of a balanced lithium supply and demand throughout this century depends on the presence of well-established recycling systems. And I know there are a lot of work going on recycling, but still there's not a single scalable recycling system which has emerged, scalable and economical. Achievement of vehicles to grid integration and realization of transportation services with lower lithium intensity. So if lithium ion is also going to go to provide heating and cooling needs, there will be significant competition happening with electrification of transportation. And so it's a question of sustainability of material supply in the future, okay? That's why we believe that thermal storage can provide that alternative, particularly when so much of energy storage will just go in supporting heating and cooling. That's why this talk will talk. I'll give you some ideas that we are working on. And then recently, Ashegan, myself, and Arun Majumdar from Stanford, we wrote a paper on 5 thermal grand challenges. Number 1 was thermal energy storage systems, which is the title of this talk, and number 5 was variable conductance building envelope. Again, sort of part of this talk, tunable transport. So I'm going to cover these 2 topics, but as you can see, a lot of this is still related of cooling and heating was another big one that we had identified. All right. So if we look at buildings where most of the heating and cooling is and most of the electricity goes, our concept is still based on linear thermal concept, which are 100 years old. So you basically have thermal Ohm's law, which is nothing but the Fourier law. Okay. So resisting, some resistance here, some capacitance here, and some storage, sensible heat or phase change. Yeah. And then only switch today that we have is an HVAC system. So you're connected to the grid and you can switch it on and off, the HVAC. In a way, that's like a switch. It's like a cooling and heating switch. Otherwise, everything else is static. Okay. So the question we ask is that if we could develop a system of non-linear thermal devices where things could change as we go, depending on ambient conditions and other changes, will it lead to a significant benefit or not? And hopefully in the next few slides, I'll show you that it will. So what are some of the non-linear thermal elements? So Chris Dames has recently published a very nice review article that you can have a thermal diode analogous to an electrical diode, could have a thermal regulator or a thermal switch, just like an electrical switch. So challenge, I think I'll show you how this can help in overall, solving energy problems. But more importantly, the question is going to be how do we develop these kind of technologies cost effectively and reliably, all right? So let me start in the next few slides. I'll basically touch upon that. If we had, imagine a world where we had these kind of devices, what kind of impact will it lead to? Okay. So this is a very nice paper which has recently come out, where if you had a variable conductance building walls, imagine that the conductivity of the walls could change. Okay, you can dynamically tune it, right, by some means and some mechanisms. Then what kind of energy savings will it lead to? So this basically this paper shows in the United States it could be anywhere between 7 to 40%, depending on climate, depending on the city. Okay, and the reason is that many times, let's say it takes an example, even if the ambient temperature is 25 degrees, inside may be very, very warm. Or even if it is 20 degrees, for example, inside may be still warm because we still generate a lot of heat. There is heating coming from your computer equipment, electronics, refrigerators, and all those things. So if we have a much better connection with the ambient and you can tune it, sometimes you get many very insulating, the walls are very insulating, sometimes they're very conducting, you can really modulate, and that way you can dramatically reduce the energy consumption. So that's one variable conductance wall can have a big impact. Next one is, as I mentioned, can we just do thermal energy storage instead of doing lithium ion or something else on the supply side? So on-site thermal energy storage. So for example, Stanford campus today gets almost all its heating and cooling by getting these two tanks are chilled water. So they take cheap electricity in the night and then make chilled water or hot water for heating. And that's how they get the heating and cooling in the campus. I mean, that's good. This is a large system. You can afford to have it in a campus. But the question is, can you do the same thing in a small building, right? Or an apartment complex? And that's where it becomes a little challenging. Well, we had published almost 10 years ago a paper that if you look at energy density of thermal energy storage, you have two types of storage. One is thermophysical storage, that is thermochemical storage. And what we found out, the thermophysical storage is really good in volumetric energy density. Thermochemical storage is really good in gravimetric energy density. However, here, lithium ion is some here, which has both very good gravimetric and very good volumetric energy density. So the question that we posed was, what can we find here? That can lead to significant, innovations in thermal sciences, thermal energy storage. So there are many different strategies. Okay, one is that maybe you don't need a very high energy density because you can distribute it in the envelope of the building because there's a lot of surface area available. Okay, and I'll show you some examples of that. So maybe that's a different kind of a system architecture. So you solve the same problem by using a different system architecture. Or you can get it here by using a lot of very innovative system design. And actually, when I was at ARPA-E, we did fund a couple of projects on that where you could use a very innovative system design and still come here, okay? Which I will not cover in this talk today. Or finally, you develop just new molecules for high energy density, and I'll touch upon that a little bit towards the later part of the seminar. Let me start with the first one, distributed storage in the envelope of a building, right? Just to give you an idea, a 2,000 square feet residential building roughly has 6,000 square feet of wall area available, rule of thumb, okay? That means if you do the math, what you find out, it can store, if you can distribute the storage in these walls, roughly 1 centimeter thick, like this here, you can store roughly 44 ton hours of thermal energy, which is equivalent to 9 hours of cooling, assuming 5 tons of cooling, okay? That's huge, right? However, the challenge is that you're going to store the energy here, and then if you don't have a thermal switch, it's going to leak. Say in the night you cool it, you store all the cold energy storage here. But if there is no thermal switch, it's just going to leak its energy on its own, and you don't have much of control. Okay, and that's why storage, the switch becomes very important. You can really control the release of the energy or control the charge when you want to charge it, right? So here is an example of how a switch and a storage can help. Okay, now this came from my colleagues Nelson and Swen. Mume Swen is at our Buildings Technology Office, in Buildings Technology Office in DOE, and then Ravi Kishore is a scientist at NREL. They analyzed, say you have a switch, you have a phase change material, here's the insulation, here's the external wall. All right. that this has been tried without a switch. People have tried putting phase change material to shift the solar load on a building, right? Here is no switch, no phase change material. This is what the cooling load looks like. So in the night time, you don't need any cooling, negative cooling load. You actually need heating, right? In the daytime, you need cooling, right? This is the cooling load positive. And then when you put a PCM without any switch, there's a little bit of a shift. You can store some energy, cold energy in the night, and then you can use it to shift and reduce the load during the day. So this is the blue curve here. So you go from 0.52 kilowatt hour for this particular system analyzed, goes to 0.37. So there is some benefit, 15% or so. However, still what happens is that, there's some leakage happening, right? Because you don't have any control. So even though you store the energy, but still start to leak the energy out. Imagine if you had a switch and you could switch it on and off, okay? That means you can completely control the release of the energy as well as leakage of the energy. And there's a dramatic improvement in the energy efficiency. It goes from 0.5 to almost 0.05, 0.1. So which is a huge 5x change, right? So that's the biggest advantage of combining switch and phase change material together. That's one. Another challenge is that if you use a phase change material with a fixed temperature, there's a problem because the ambient temperature changes. So people have tried putting phase change materials on the envelope. Okay, there's an actual demonstration happened in a building. This is the data from a real building. Percentage of the days out of the year fully active. That means fully active. That means the phase change material is melting completely and then solidifying completely. Melting completely, solidifying completely. 0%, never happened. Partially active, 36%. That means sometimes melted a little bit, then solidified, melted, not, but never completely melted. Same story in the east wall as well. And then there's a simulation shows from the colleagues at NREL that they simulated for some, I don't remember the climate zone, but bottom line is almost 80% of the year, the stores were inactive because the ambient temperature was changing and the storage temperature is fixed at which the melting happens, okay? Here it is happening. You can see the phase change indicator means one means, completely solidified and 0 means completely melted. Melting, solidifying, but in between completely inactive, okay? That means I'm not using the storage. That has a direct cost, storage cost. The levelized cost of storage is going to go up. That's where I would say that tunable transition phase change material, if you could match it with the ambient temperature, can help you dramatically in cost of storage. And the reason is very simple. Levelized cost of storage is roughly inversely proportional to number of cycles you're charging, discharging, and depth of discharge. This is a terminology used in battery community. Depth of discharge in case of phase change material would mean that you're going all the way from molten state to solidified state to molten state, right? And if you're doing it completely, if you have a, let's say, centimeter thick material and all that centimeter gets always melted and all the rest gets solidified, that is depth of discharge of 1. And if it never melts, then depth of discharge is 0. So if you define something called a utilization factor, that means you're utilizing more. It's like n multiplied the average depth of discharge, because most of the time you're not going to do a depth of discharge of 1. Like it's not going to be that the whole material always melted. So there's a paper that came out from Swen and Nelson where they showed that if there was no tunability, you have fixed transition temperature of a phase change material. Many times it's too cold to activate, it never melts. So many times it's too hot that it melts and it never solidifies, depending on the ambient conditions. And then in between, you have back and forth of cycling as well as partial melting, partial solidification. Whereas if you have a really good tunability and it's matching the transition temperature, the melting temperature is changing with respect to the ambient temperature, you can see the number of times cycling, number of cycles has dramatically increased. It's going back and forth, and average depth of discharge also increased. So they found out the utilization factor increased by roughly 20x. That means the levelized cost of storage went down to 20 times. So that's where tunable transition temperature can help you dramatically, right? All right, moving on. Now the question is, what are some of the fun? I hope I have showed you that if you can develop these materials, that's great. But the question now is, why not? Why hasn't it happened so far? So there are some fundamental and applied questions in thermal storage and heat transfer fluids, which we need to solve, and which I think makes it very exciting for us as a community, that we can, if we solve these things, it can have a huge impact. One is, first of all, how do we design new phase change materials? So modeling and prediction of latent heat of fusion, right? That I think will help us a lot in designing new materials. Second one is, how do we solve and specify metastable performance of PCM, which is basically supercooling. They are in metastable equilibrium, right? And I'll show you later, which is a very, very well-known problem in this field. And finally, how do we design the next generation of materials with tunable phase change temperature or enhancing heat capacity of liquids? So let me start with the first one, latent heat of fusion and vaporization. There's a very well-known rule called Troughton's rule, which is empirically derived. So what I'm showing you on the y-axis is enthalpy change, and x-axis is the temperature of melting or vaporization. As we know that first order phase transition, delta H is equal to T delta S. So if I plot delta H versus T, the slope is basically delta S. And so Troughton figured out that empirically that this delta S is nothing but is almost 10.5 times the gas constant. Okay. And then there's something called Richards rule of melting, which is the delta S average, the slope is 1.1 R. But as you can see, there's still a lot of scatter around it. So the question is, how do we explain this? And if we can figure it out, then maybe this will help us in designing new materials. However, it is very challenging because as we all know, modeling liquid thermodynamics is very challenging, and most of the work happens using molecular dynamic simulations. And the reason is the potential energy surface in liquid is very complex. Okay, one hand you have solid-like vibrations, which basically is just like a parabolic potential between atoms. Then another one is small-scale diffusion, which basically happens is that, let's say you have parabolic curve here between the atom, just like in solids, but the equilibrium position itself shifts at different time scales. So sometimes it is here, as you can see here, sometimes it is here. Okay, so that's called a small-scale diffusion. Okay, and then there's a gas-like diffusion, which basically means it goes from one point to completely different point. It switches from here to here, for example. So so that makes the potential energy surface and liquids very, very complex. Okay, and that's why a lot of molecular dynamic simulation has gone in explaining some of the liquid behavior. And then finally, there is also a lot of, even though you have lattice vibration, which is solid-like, except they exhibit in liquid state, they have larger level of enharmonicity, right, as compared to the solid state. Okay, and then I already talked about large-scale diffusion, which goes from this point to this point, and then you have small-scale diffusion, which is basically movement of the equilibrium position. Anyway, so we have tried to model it analytically so that we can figure out what really affects the entropy change at melting. We made certain assumptions. First of all, we assume that at melting temperature, enharmonicity can be neglected. Basically, there is enharmonicity in the solid as well, but again, it's much smaller compared to in a liquid state. So right at the melt point where it melts, we assume that enharmonicity is very, very small. And actually, there has been some molecular dynamic simulation which suggests that that is a really decent assumption. Another one that we assumed is that at melting, the large-scale diffusion can be neglected. And this is only valid if there's something called a Frankel frequency, is much smaller than the Debye frequency, which basically fails for noble gases. And it basically translates into that if you have a highly viscous liquid, this is a very good assumption. If it is a low viscosity liquid, then it is not a good assumption. Okay, so that's the reason is falls for noble elements, right? And then for temperature greater than melting temperature, we use the phonon theory of liquids recently proposed by Trachenko and Braskin and co-workers, right? To basically figure out entropy of melting and then how does it change with temperature of the liquid. So here it is. First of all, as I said, we are only looking at the small scale diffusion. So I won't bug you with the math here, but imagine that you have a parabolic potential like in any solid. And imagine that the equilibrium position also is changing. So we have assumed that the equilibrium position also changes, has a simple harmonic motion, okay? And then there another assumption we made is that the amplitude of change of this equilibrium position is same as the amplitude of the atomic vibration. And again, there is some molecular dynamic simulation which says that it's of the same order of magnitude. In this case, we just assume that it is same. And so when you do that math, what you find out that the effective frequency of the atom here is omega d by liquid, it's on the liquid side, divided by the square root of 2. That makes a big difference. This is what this simple math and assumption turns out to be, that you divide the divide frequency on the liquid side by square root of 2. Now the question is, what is the divide frequency on the liquid side? So the first order estimate is, you can just assume it is same as the solid. This is right at the melt, right at the melt time temperature. However, that's a rough estimate, really not very accurate. The true divide temperature frequencies have been calculated for some of the elements, monoatomic elements, as we are discussing here. So whenever that's available, that's great. We should always use that. However, it's not always available. In that case, we have used the quasi-harmonic approximation, which basically tells you that if you know the density, so there is always going to be a slight density change at melt from the solid side to the liquid side. And if you know the divide temperature on the solid side, then you can use the quasi-harmonic approximation to calculate the divide temperature on the liquid side. All right. So now once we have that, then we calculate entropy, absolute entropy. Okay. So for this is the standard formula of absolute entropy of a classical harmonic oscillator, which depends on the frequency of the oscillator. In case of the liquid, as I showed earlier, this will have the square root T and omega dl. So now I can calculate the entropy change from solid to liquid, and it just turns out to be this simple formula here. Okay. So now here you see we are comparing it with the experimental entropy of fusion with the prediction. It's very, very good match. I want to point out that the blue ones here, the match where the match is very good, is based on getting the exact divide temperature from literature for some of these liquids. These ones, the black ones, are based on the quasi-harmonic approximation. Here's another blue one, okay? So this spans very, very good. So I think if we have more accurate information on the divide temperature of the liquid, then the match will be even better. Just to tell you, the Richards rule that I showed you earlier is the constant number 1.1 times the gas constant. That turns out to be just a flat line, a 1 point number here. Okay, this is the dotted line, right? Now the question is, okay, so now we have described the entropy of melting. That means I can also describe enthalpy of melting. How does it change with temperature? So what we have done here is that we just calculated in the earlier slide the entropy, absolute entropy at melting. And now if I know the heat capacity of the liquid as a function of temperature, then I can use the second term here to describe the variation as a function of temperature, okay? So as long as I know the entropy change, right, absolute entropy change right at melt. So this has been calculated by Trachenko and Braskin, where you have an n-harmonic term. There's a loss term associated with loss of transverse phonons, as we know that liquids cannot support shear waves, shearing. So there's a loss term associated with the loss of transverse phonons. And then we have also added an expansion term to account for if you want to calculate it at constant pressure, then the liquid is going to expand. So we got to include an expansion term in the entropy change calculations. So I won't bug you with the math here, but it's given in the paper. But the bottom line is that the match is very, very good with respect to temperature, okay? Where omega f is the frontal frequency, right? So this matches very, very well as a function of temperature. So now once I know as a function of temperature, that means I can also predict the absolute entropy right at vaporization, just before vaporization, right? So we use that, and then now we are calculating the entropy of vaporization. So as I showed you earlier, Tauten's rule is again an empirical rule. It's just one number. It is 10.5 times the gas constant. It turns out to be here, whereas this model provides the correction depending on the material type. And the way we calculate latent heat vaporization is, we calculated the entropy of melting, from the liquid side right at vaporization. And then on the gas side, we just use ideal gas laws to calculate the absolute entropy from the gas side, and then we calculate the delta. However, so this basically has developed a decent model, but again, future work will include how do I relax the assumption for low viscosity liquids. Right now, we have assumed the Frankel frequency is at melting temperature, it's much lower than the Debye temperature. And then how do we develop it for multi-atomic materials? Okay, because then you have to understand interatomic vibrations. And finally, how do we calculate the liquid Debye temperature without going to molecular dynamics? Okay, right now we have a quasi-harmonic approximation, which works decently well, but are there some other ways? These are some of the open questions. Moving on, metastable behavior, supercooling of PCM, very well-known problem. I mean, the whole community knows this, who has ever worked on phase change materials. So, you know, what happens is that the melting happens at one temperature and solidification happens at another temperature. Okay, and this is the data from our own group, and this is the data in literature. Basically, it has a direct impact on energy efficiency of storage, because what's going to happen is that let's say you're doing cold storage, you will have to use your heat pump to go to a much lower temperature to make this thing solid. But when you get the energy back, you're going to get it at a much higher temperature. Okay, so you do the math, and there's a huge round trip efficiency, right? So that has a direct impact on cost of storage. So solving this is another very big. Will have a huge impact on at the system level. But the challenge is, what do we do in our lab? We measure things in a DSC, and then we do measurement at 10 microliters. That's the order of magnitude, right? At the scale at which we measure the material. At the system level, you're going to use multiple liters, right? Tons of these materials will get used. So the question is, how do I translate the supercooling behavior at the lab scale to what's going to happen at the system scale? Okay. And then also lab scale, you do in isothermal case. It's a tiny material, so everything is isothermal. At large scale, there will be temperature gradients. Already there is empirical evidence that measurement done in DSC versus measurement done at system level, they don't match, right? So that's a big problem in developing technologies. So the question is, how do we figure out the performance at system level, and while we do the measurement in a DSC at a 10 microliters or so. So we all know this. Fundamental understanding of supercooling metastability still remains a grand challenge. There is nucleation theory, right? So you can figure out nucleation theory, but again, there are so many unknowns in that nucleation theory. So mechanism is understood that you need, there's an activation barrier to get your nucleation barrier. But the question is, can we really use it for predicting performance at system level, right? So you have supercooling changes with geometry, volume, material, microstructure, purity, discharge rate, vibration, I'm just name it, right? How do we predict the performance of these materials with all these variations and at large scale? And that's where I would say that we have taken an approach, a statistical approach, which combines nucleation physics with some statistical measurements, okay? This approach has been used in fundamental nucleation studies of metals and its solution crystallization process, but has never been applied for PCMs to the best of our knowledge. So what you do there is that you experimentally obtain the nucleation rate, which is JVT, by developing, measuring this, figuring out this chi-t, which is a survival function. I'll show you next slide, how do we get a survival function, okay? So you get a survival function experimentally, and once you know the survival function, you can then figure out the nucleation rate, and that will help you a lot later on predicting the behavior of these materials as a function of different parameters that I talked about. And then you get this, and then rather than using it directly, then you fit it using this kind of a formula, which really helps in solving something analytically. I'll show you later. And then that's how we predict the performance. So let me talk about a survival rate. By the way, one more big difference is in metals, it has been used. Metals have very high thermal conductivity, so the temperature gradients don't make a difference. in phase change materials used for energy storage, thermal conductivity is much lower. Even if you put graphite and other things to increase the conductivity, still much lower than metals. So temperature gradients will play a very, very big role, and I'll show you an impact of that as well. Because that's one of the big difference between the metals and the phase change materials. How do we get a survival function? So what you do in a DSC, I'm showing you actual data, raw data here. You take the material, same sample, you measure it multiple times in DSC, multiple times, very rapid measurements, but multiple times. And since nucleation is a statistical process, what you will find out is that different measurement solidification will happen at different temperatures, okay? So for example, you see here, the blue line here, this light blue, solidification happened roughly at 29 degrees or so, here roughly 29.5, I would say. And look at the pink line here, I'm not sure if they can clearly see it. Here the solidification happened roughly at 27 degrees, right? Right. So this is same sample, just multiple measurement, multiple times, right? So how do we calculate the survival function? So below, we could not get any solidification below this 29 degrees or so, okay? So that means everything survived, nothing solidified. So the survival function is 1. So that I'm showing is supercooling with respect to T melting. So I believe T melting in this case was around 40 degrees. So roughly 11 degrees or so, everything survived. That's a supercooling temperature relative to melting temperatures. We are taking the difference. Then you go here at 27 degrees or so, nothing survived, right? Everything solidified. So the survival function is 0, okay? Then you do this multiple measurements, you get a survival function. And then what you do is that you look at the change of survival function with respect to the temperature, with respect to delta T, the supercooling, and you can calculate from here empirically the nucleation rate, where V is the volume of the sample and beta is the cooling rate that you use in your DSC, okay? And then we fit it using this formula here, gamma delta T to the power n. Of course, you look much more scattered here because this is a differential of the survival function. Whereas if you look at the same fit here, this gamma delta T and here in the integral, it looks very, very smooth, right? All right, so once you have that, what you can find out is from this formula here, you know now gamma, you know n, so this fit, I can find out the average cooling rate, average supercooling, which turns out to be a function of the cooling rate and the volume of the material. And then you can also find the average time to nucleate. What it tells you here is, it's very simple. If the average cooling is slow, like really quasi-steady state, like we do very slow, very close to equilibrium, delta T average goes to 0. That is the equilibrium thermodynamics. There is no finite kinetics here, okay? It's kinetically very, very slow. You will not expect any supercooling. If you make beta very, very large supercooling, okay? And we see that experience here. So you have beta here versus 10x change in beta, and then suddenly the supercooling increases. Volume, if you're larger volume, you have more nucleation sites available, the supercooling should decrease. And we clearly see it. We varied the volume by orders of magnitude and the model fits very, very well, okay? But here's the challenge though. First of all, this is isothermal still because we sit in DSC. I'll talk about non-isothermal case next slide. But the challenge here is that whenever we read papers and when we see that spec supercooling, it needs to specify exactly the cooling rate and the volume. Otherwise, supercooling is a strong function of the cooling rate and the volume of the material used. And that basically tells us that there is a need to develop a specification to characterize any phase and material where supercooling is being reported. All right, moving on. In reality, if the material is very, very thick, it's not going to be isothermal. So we solve simultaneously, use this equation here, which you obtain from DSC. Then you apply for the heat conduction equation, and then you solve it simultaneously. And then by using this as a nucleation parameter. But we did some experiment where we kept the volume of the material constant. This is the volume of PCM, but made it thicker. So here it's very thin, and it is very, very thick, where temperature gradient becomes very, very important. And then we solve it, we compare it. So this is the lumped constant cooling rate, which goes back to this formula here, versus actually solving the temperature gradient using the thermal conduction equation. And you can clearly see there's a huge difference in time to nucleate, okay? So again, at the system level, you got to use this and combination of this. So you can get this experimentally, and at the system level, you can get this. You can solve it for any system. You need to know the thermal conductivity, and then you can actually predict what is going to be the supercooling behavior at a system level. All right, moving on, tunable phase change materials, as I mentioned, can be a potential game changer. Ideally, what you really want is your phase change temperature sort of changing with changing ambient temperature. And if you can do that, you can have many applications, either in buildings, as I mentioned, even power plants. There was a nice program launched by ARPA-E where you can use phase change material to enable dry cooling of power plants. So you can store energy in the night and release it during the day. Again, so the ambient temperature makes a big difference. So one of the solutions that we have proposed is that we're using ions. As we know, you can use salt to melt snow. In an icy condition, we use salt to melt ice at a lower temperature. Similar idea here, except the challenge is, how do I make it dynamic? So how do I make ions go in and ions come out dynamically? Go in, come out, right? So that's why we have leveraged a lot of our learning from the battery world. So here you have ions in the phase change material, and it will melt at a lower temperature. And when I pull the ions out, then it will melt at a higher temperature. So we did some experiment, first of all, statically, just mixed different salts and did DSC. And you can clearly see that this is increasing salt concentration, and the temperature at which melting is happening is decreasing, okay? So that is pretty, very well understood. Then we applied Flory-Huggins theory of polymer solutions to understand some of this behavior. Challenge is, how do I do it dynamically? That is what we have done. We have developed a cell where this blue area here is the phase change material. All of this is phase change material, and the salt ions come in and out, and this is the charge discharge behavior of this cell, right? And this is the temperature change, or the melting temperature change. We have achieved roughly of the order of 5 to 7 degrees change dynamic tuning temperature right now. The paper is under review. I think there is still a lot of work needs to be done. Again, can we increase the temperature band further, and also cyclability and a few other things. So again, but I would say this is, at least from our group, this is the first demonstration of changing the melting temperature using ion, dynamically changing the melting temperature using ions. All right, let me move on. I'll take 5 minutes or so to quickly go through certain things. We all know that heat transfer fluids play a very, very big role. I don't have to tell this community. However, most of the heat transfer fluids are van der Waals bonded molecules. So you have the bond energy is roughly 5 kilojoule per mole. Water has the highest heat capacity. 70% of the heat capacity is due to hydrogen bond breaking, 10 to 30 kilojoule per mole. Question is, can we use covalent bond breaking, which is greater than 100 kilojoule per mole, to beat water and achieve higher heat capacity? And also, water has a challenge, as we know, 0 degrees Celsius is the freezing temperature, 100 degrees Celsius is the boiling temperature. So it was proposed, Diels-Alder chemistry, which is very well known in chemistry community, was proposed as a storage as well as a heat transfer liquid in late 70s and early 80s, but there was no experimental demonstration at that time as far as we know, right? And the advantage of this Diels-Alder chemistry is that they typically occur in liquid phase, and they typically have very high reaction enthalpy and very high entropy change, which is, both of them are very important, because high reaction enthalpy enables higher energy density, and high entropy change enables that you can tune it at a manageable temperature, near ambient temperature, okay? So here's we are excited that we got the first data out on one of the molecules where, first of all, this freezes at -60. Actually, did not even freeze even there. We could not go below -60. So very, really low freezing temperature. It boiled at around 130 degrees, so goes beyond 100 degrees Celsius. The most exciting thing we found out so far, that it is able to beat water. Right now it's a narrow range, but it goes above water heat capacity. And it is definitely much, much higher than other types of heat transfer liquid. For example, mineral oil is right here. Much higher heat capacity on some of the antifreeze liquids like ethylene glycol and propylene glycol, right? And another important thing is that the viscosity also is much lower than other liquids, except it's higher than water, but not as high as other liquids. So that's another important factor on this, right? So this is very exciting in that sense, and hopefully, we should be able to expand the band further. We have done some DFT simulations, which has told us matches fairly well with the data. So the DFT is enabling us to look at new molecules, how we can change it, expand this band further. Since we are talking about tuning, we have done static tuning of Beal's order. So basically, by putting different functional groups on the molecule, you can change where the peak heat capacity happens. This temperature versus this temperature. Here it is happening around 110 degrees. So that's more of a static tuning. I will skip this slide, but potentially you can do dynamic tuning. There's a paper which has come out. Chemistry community, they have been looking at it, and they can apply electric field and you can dynamically tune where the reaction kinetics. So potentially you can do the dynamic tuning as well. I'm just going to spend a couple of minutes on switching. Okay, as I said, thermal switches can also play a very, very big role. So recently there's been a lot of activities happening on electrochemically switching thermal conductivity. And I would say, to the best of my knowledge, I'll give credit to Professor David Cahill at Illinois. In 2014, they published the first paper where they took a typical cathode material which is used in lithium-ion batteries, lithium cobalt oxide, and they showed the lithiation and delithiation changes the thermal conductivity of the lithium cobalt oxide. So you can see it goes from 5.4 to 3.6, depending on the lithiation, delithiation of the lithium cobalt oxide. So that was already showing that you can tune it, the thermal conductivity of these intercalation compounds. Then recently, Gangchen's group had come up with another electrochemical tuning of the thermal conductivity of strontium cobalt oxide, where the stoichiometry can change depending on the voltage applied. And they got a contrast of roughly 2.5x, going from all the way from roughly 1 watt per meter Kelvin to roughly 2.5 watt per meter Kelvin or so. Ken Goodson's group at Stanford, they look at molybdenum disulfide, and they measure an overall conductance change. Roughly, the contrast was of the order of 8. Okay, and then recently we have been looking at, this is a commercial battery, actually lithium-ion battery. We looked at the thermal conductivity of the anode as a function of state of charge, where we see the thermal conductivity changing from 1.3 to 0.9. Although our motivation is not on thermal switch, our motivation is more on understanding lithiation and delithiation using some thermal signatures. Okay. So, bottom line is, so far, whatever I've seen in electrochemical tuning, I think I've seen the contrast going all the way roughly from 2x to 10x at most, right, in electrochemical switching. I really think that contact, decontact, it's really very hard to beat, right? Where you are contacting a surface and decontacting a surface, contacting a surface and decontacting a surface. So Professor Chris Dames had recently a paper come out on thermal management of batteries, which is very interesting. That, as we know, batteries in a very cold climate do not work very well. And also if battery gets hot, it doesn't work very, very well. So there's a sweet spot of temperature. So Chris's group figured out a shape memory alloy-based thermal switch, when during the cold climate, if it's very cold outside, it completely detaches itself from the heat sink. So it's like thermally isolated. And then once the battery starts working, it starts to generate heat. It goes and connects itself to the heat sink. So you need a switch. They actually found out that this contact-decontact switching using shape memory alloy, they got a ratio of roughly 2000:1, which is huge. Makes sense because again, it's contacting and decontacting. We have used a similar idea, and Chris and I are working together on adapting the similar idea for buildings, and also trying to make it very, very cost effective so that it's very scalable. So far, we have gotten a switching ratio of 35, which I think is pretty, pretty good, because based on some of the results I already showed you earlier, that's a really good switching ratio for building application. And R value, which is the actual absolute thermal resistance in the off state, is roughly 2.5, which is pretty decent for building insulation applications. And we are also working to take that R value more than 2.5, so to increase the insulation value further. So I think I'm just going to stop here. I just wanted to, hopefully I gave you a flavor of both, what the impact could be, what are some of the fundamental questions, and what are some of the practical ideas. And then I will be just happy to take questions.
Thank you so much, Ravi. Just want to remind everyone, if you've got questions, please put them in the Q&A box. We'll be fielding sending some questions to Ravi now. I'll start with, I guess, a question that I thought was kind of interesting. I was particularly interested in kind of your high-level view about, with a lot of these technologies, I mean, at the end of the day, the heat that you're talking about scavenging or saving is pretty low value to begin with. And so what are your thoughts on the chances that one will be able to actually make any of these ideas work economically, because the value of the heat's so low to begin with? Like, it's a difficult application, because you almost by definition, right, like the energy density is low because the temperatures are near room temperature. So it's not like you'll be able to bring some super high energy density materials into play here. And then at the same time, you because you're dealing close to room temperature, the power density is low. So you almost by definition have to use lots of material, like for whatever it is, any kind of storage, it's going to be, a pretty large amount of material. And so that pushes you towards having to use really cheap materials. And so I'm curious, what are your thoughts on the likelihood that we'll be able to find some solution that's low cost and can offer some benefits in some of the ideas you have?
So that's first of all, heating that we use to keep our buildings comfortable is already low value to begin with. You're not trying to boil your human beings, right? So you want to keep it 25 degrees. That's your need. You don't have a way out of it. So as I showed you earlier, a lot of your energy storage, doesn't matter where you put it, whether you put it in the grid, put it in electrical form, doesn't matter. That will be going to supplying a low quality heat, because that's what is to keep you comfortable. So that, I think, is not an issue there. I think the question that you're asking becomes very important when people try to convert that low quality heat to electricity. That's a very different matter altogether. When you need heat, at the end use is heating, then anyway low quality is okay because we need it, right? For buildings. For industrial is very different, okay? Now the question is your material. Yes, that's a great question. Again, it's going to be, as you and I were discussing earlier, economics will dominate finally. I mean, that's my bottom line. We want a renewable world, but we want affordable energy. I mean, there's no way out of it, okay? So the question is that, okay, either I distribute a lot of cheap material across the building envelope, that's one way, so I don't need very high energy density material, okay? That's one strategy. Or I have dirt cheap material, okay? I mean, people are using water. Right now, people are trying to use water. I can heat water in a water tank. Challenge with water is that, again, you cannot keep it, you have to keep it inside your garage because otherwise it freeze. So again, ideas like, something which you can put outside in the backyard, and if those materials are much, much cheaper, which I did not show you here, that we are working with NREL, Oak Ridge, and LBNL together. We are developing a levelized cost of storage framework where the input energy is electricity and output is thermal, okay? Because that's what it is, thermal. You will need thermal energy. Then you compare electrical storage versus thermal storage, and then it depends on situation where thermal storage will dominate quite a bit. But I did not show it here because we are still doing a lot of analysis. So again, question is very fair. I think the game is on right now. Nobody can say right now which is going to win. It's going to get dominated by economics and sustainability material supply, which will again dominate economics. I mean, if you don't have sustainable material supply, then it's going to impact the cost.
Okay. Yeah. Another question is with regards to the phase change materials and I guess the question is like, really, how big is the design space from the standpoint of possibly finding other molecules or other reactions? You mentioned the Diels-Alder reactions. Like, how many are there? Like, is the design?
That we have a lot. That is in the Diels-Alder space. You have a lot of possibilities. Okay, it's like it takes me back to my high school chemistry when they used to ask you go from one organic molecule to another organic molecule, there are 20 different pathways to get there, okay? So you have a huge design space there.
Mm.
So that I would say is, that I think has been very exciting for us. I mean, I didn't show you here because we have not published it, but we already have data on 7 or 8 different substitutions, which tunes it is a different.
You said how many?
7 or 8 different substitutions.
Wow.
Yeah, that I think it's just chemistry field is just full of it because they have mastered it for so many different applications. Yeah.
Interesting. Another question that's come up is really about, and this I guess goes back to this notion of cost being king. You talked a bit about the energy density being low, but then this also, you got to deal with the heat exchangers or whatever is going to help you get the heat in and out. Low power density, you're dealing with low delta T's, you're close to the room temperature. Do you have any thoughts on, are there any new opportunities, or can you speak to like the costs of the heat exchanger?
That I think is yes, that is a great question. Let me just say that first of all, I did not touch upon it. That is a very, very big question. So look, let's just face one thing. Let's be honest. At the end of the day, we have to dump it to air. Okay. So I mean, that's a fact. Okay. There's no way out of heat transfer coefficient of air. Okay, so there's no way out of just increasing the surface area. Okay, I mean, so one thing is that you do it when in the envelope where there's a lot of surface area already available, because they have a lot of surface area available. So that offers one unique advantage. Again, there are challenges. I don't want to underplay the challenges. That has integration challenges.
Mm-hmm.
Okay, but on the other hand, you also have particularly if you have thermal storage, which is compact, not distributed, right? Then again, you just like what you have in your, air handler units, right? I mean, today, if you look in the US, for example, you have air handler units. In your air conditioner also, there's not huge delta T available as such. So you still have air handler units and you have heat exchangers. So I think you will have to use those heat exchangers. And I mean, if you look at air conditioning today, I mean, typically, the evaporator temperature is 5 degrees Celsius or whatever, right? And then your room temperature 20 degrees. So that's the maximum delta T available to you, right? So again, that way, the PCM, what temperature you melt is both the heating side and the cooling side will depend a lot on how much delta T can you afford between because to have an affordable heat exchanger.
Yeah, I mean, I guess thought that comes up with that, I guess I had not previously really thought of it, but I guess it's the same, just like with grid scale storage, you have like a cost per unit energy and a cost per unit power. Same is true for thermal storage in the context of heating and cooling, right? I mean, we often talk about the cost per unit energy, but what about this cost per unit power portion, which is these heat exchangers? Do you have any insight into which one is likely to dominate?
Yeah, so I would say, first of all, let me take back. Already there is a really good paper came out from NREL. Jason Wood, Roderick, and a few other people. They designed a Ragone plot. There's a paper which came out in Nature Energy recently, exactly to answer sort of your question. Mm-hmm. As you know, Ragone plots are very well used in battery community. Mm-hmm. So the power density and the energy density, right? So they have a very nice plot. I have not read the paper in detail, but I think that's the first step where I would go and start looking into and start creating those curves, right? I think it's going to be still dominated a lot based on some of the stuff that we have done on the levelized cost of storage. I think it's still dominated more by the storage material right now than the heat exchanger itself, okay? Because I would say that heating and cooling community is very well aware of the people, the practitioners of the art are very well aware of heat exchanger costs, okay? Challenge, again, I will say this, and I've always been saying that, I think you and I have discussed this. As soon as people start talking about converting it to power, the economics changes dramatically, okay? Because you have to divide everything with the depending on what you are, by the Carnot efficiency at best.
Yeah, of course.
Right, and then, in my opinion, things become very, very different.
Yeah. Another question that came up is about handling. You talked about handling sensible heat. What about controlling moisture? Do you have any thoughts on to what extent there are new opportunities in um, switchable materials or switchable systems where you can actually do this for moisture control?
I think that's a great question. I mean, I think I'm not. I know that Buildings Technology Office has a lot of interest on things like moisture diodes and stuff like that, so that you can basically take one-way transport of moisture or molecules. I believe membranes are, in a way, are suitable of doing that. Have I seen I mean, let me step back. When I was at ARPA-E, I funded a couple of projects on membranes, some of them doing really, really well. Okay, that was basically to handle the moisture load itself. The question is that, is there something passive, which I'm not aware of right now? But actively, I've seen people really using membranes and sucking the moisture out. In fact, may be aware that there's a global cooling prize competition going on in the world, and they're going to announce the winner on end of this month, 29th of April. And if you go and check out their website, I've seen 2 or 3 projects where they have, there's not much description. Of course, these things are confidential for the companies, but I've seen at least 2 or 3 projects on membranes where they're trying to separate out the latent load from the moisture load. Yeah. Sorry, the moisture load from the sensible load.
Mm-hmm.
Yeah.
Another question. This is I think, an interesting practical question, which I mean, is a big question. At least I know in the context of thermal storage at high temperatures in the area I work in. I never really thought about it in this context. But what about the volume change when you do these phase change materials? Do you run into any issues of possible damage to the container walls or the walls themselves due to the repeated volume changes there? Are they wetting or non-wetting, or can you place them within a non-wetting layer so that they can expand and contract, and you leave maybe an air gap? And how do you manage all that from a practical standpoint, this volume change?
I have not seen. First of all, the temperature swing is very small, right? So if you just do volumetric expansion itself, when you go to high temperature, you go from low to 1,000 degrees Celsius. That's a huge delta T.
No, this is about, I guess, right around the melting point, meaning going from solid to liquid.
No, I hear you. I think the challenge has been, there are different challenges. That's why you put it in a leakage is an issue. Okay, so people have tried to put it in what is it called? Encapsulation. Encapsulation is a way both to enhance the surface to volume ratio, to enhance heat transfer, as well as to contain it. Okay, and there have also been ideas of using porous graphite layers and stuff like that to contain the material inside it, right? And then you have enough free volume available to expand it and stuff, right? But leakage has been an issue, and another thing which I did not touch upon is another area that we have been looking into is complete solid state phase change. So you just go in remain in solid state, okay, so that you don't go through solid liquid phase change, but you still go through a phase change, and it goes from one state to another state, but remains in solid state. So there are different advantages as well. Except when you remain in solid state, then enthalpy change is a little lower. I mean, there's no way out because you don't have that much of entropy change. So delta H, as I discussed earlier, is T delta S, so entropy change is not that high. But there are advantages though, that you don't have to worry about leakage and stuff.
Yeah, one other question I had. There was a slide you showed with a material that had a higher heat capacity than water.
Yeah.
I was curious on that particular slide. I noticed your units were joules per gram per Kelvin or degree C, and I was curious if you still get that same, if you manage to beat water on a molar basis. Because I guess you do have this potential to play games with the units here, right? Like if you choose a light enough molecule, right, you might be able to win on a gravimetric basis. Do you know? Have you checked if that actually exceeds water on a molar basis?
Let me put it this way. First of all, I don't like molar basis.
Really?
From engineering point of view, that is not at all important. From engineering point of view, volumetric, actual volume, and actual weight matters. Moles don't matter.
Yep, agreed.
Okay, so that's why actually on a molar basis, you will see the latent heat of vaporization is beautiful, 40 kilojoules per mole. Volumetric basis, you will never use the latent heat of vaporization to any energy storage. Okay.
Yeah.
So in that sense, I would say that gravimetric is very important. Okay. And then volumetric also is very important, and where we are again same as water because it's organic molecules. There's not much density difference. Okay. So these are the two things. I think I can go back and look at I'm sure because the postdoc, Pei-Wan, who is not a professor, he's a fundamental chemist. He when he came in the group, he used to talk in molar basis, and I corrected him. I'm like, I'm not interested in molar basis. It's a really good for chemists, not good for any engineering. So I think I can go back, but I'm not sure what I can do the conversion. But gravimetrically and volumetrically is the right thing to look from technology point of view.
Yeah, it's interesting. I have an interesting perspective about this. I'll share. I mean, I guess I agree with you, and at the same time, the reason we use molar basis is because we reference all costs of materials on a molar basis, because you can play tons of games, right? With the span of weights on the periodic table is like a factor of 100. And so if you look at cost per unit weight of different elements, you'll convince yourself of all kinds of things that are incorrect. But if you just look at it on an atomic basis, it's a little easier to normalize across all these things. But that's the reason we use it. But I 100% agree. At the end of the day, from a technology standpoint, weight and volume is what actually matters.
Yeah.
Volume, I think, doesn't change dramatically across the periodic table. Most atoms are a couple angstroms apart for condensed matter, so they fall within this, within one order of magnitude. But weight, in particular, can change dramatically across the periodic table. So,
yeah, I mean, I think what is the highest weight density material? I don't remember now. It's like,
I mean, so for example, we work a lot with tungsten, right? Tungsten is 18 times more dense than water.
Yeah.
All right, so I think this may be a good stopping point. I want to thank you again, Ravi, for this excellent talk. It's an amazing talk. I think it's extremely thought-provoking. We really appreciate your perspective and teaching us a bit about what you've been up to. Let me go ahead and share my screen so I can show this last reminder slide. So just reminding everyone once again, next webinar is going to be April 28th. It's on opportunities in nano-engineered surface designs, a panel, and we hope that you're able to make it. Again, please put any suggestions for future topics that you might have in the Q&A so we can take a look, and you're strongly encouraged to please sign up on the email list to get notifications about future sessions. And again, all the past events, videos, Q&A are all on our website, inotherm.mit.edu. So with that, thank you very much, Ravi. We really appreciate, again, your giving a talk today. And it was very, very thought-provoking and intriguing. Lots to think about.
Thanks a lot, Ashray. That was great. Fantastic.
Yes.
Yeah.
Take care. Thanks, everybody.